Wasabi, you guys! Welcome to our first lecture in linear algebra. Today we are going to learn Introduction to Matrices. Now, before we get into matrices, we must first learn the background behind it, and that is systems of equations. So, pretty much, literally anything that looks like this, let's say, I'm just making this up. We're not actually going to solve it because this is probably either has no solutions or it's just too nasty to solve. Let's make this negative just for realism. This is a system of equation, and you probably already learned that before in algebra. In any algebra class, we know that this is a system of equations, but just to recall, we call this a system of equations, specifically linear. So, system. This is a system, and we'll just say that for short as we continue along. Pretty much, whenever we have a system that has a solution, then we say that it is consistent, okay? It could be like, it equals to this specifically, or it has infinitely many solutions. Yes, we can have a system of equations that has infinitely many solutions. Either if it has a solution, either way, the system is consistent, and that's what you're gonna come across when you take linear algebra. You're gonna hear that word a lot when they say if this system is consistent or not. That's what they mean by consistent. Does it have a solution? Now, if it doesn't have a solution, then it's just inconsistent. That's it, right? That's all you need to know. If it has a solution, it's consistent. If it doesn't, it's inconsistent. Okay? Okay. So now you probably already practiced, but I'm just gonna help recall again. How do we solve a system of equations? So we have 3 legal actions that we can do. 3 legal actions. Okay? Try not to hit my wall. So what are the 3 legal actions? First one, multiplying an equation with a non-zero number. Okay? Obviously, you cannot multiply an equation with 0 because then you just make everything 0, and that's just pointless. So, any number that's not 0, pretty much. Number 2, switch places. On 2 equations. And then for number 3, okay. For number 3, this one's a little complicated by wording, but you'll understand when I demonstrate it for you guys. Adding a multiple of one equation to another. Okay? So these are the 3 legal actions that we can use to solve a system of equation. Now, of course, you can obviously pause this video and take note of that, but let me go ahead and demonstrate those 3 legal actions. So, what am I doing in general? So, if you've learned or practiced systems of equations, pretty much we want to delete one variable so that we can solve one of the variables. And how do we take away one of the variables? Is we try to multiply some number so that when we add the 2 equations, one variable will cancel out. So in this case, here, I'm just going to draw an arrow. So what I'm going to do is I'm going to use legal action number 1, multiply an equation with a non-zero number. And what I'm going to do is I'm going to multiply 2 here so that I get 4y So we have plus 4y minus 4y. When I add it together, that y is going to be gone. So let's go ahead and write that down. So multiply by 2 on this first equation. 10x plus 4y equals 16. And then 3x minus 4y equals to 4. Okay? As you can see, we used legal action number 1, modifying this first equation. Now we have plus 4 minus 4. If we add these two equations up, this is going to cancel out because 4 minus 4 is equal to 0. And 0 times y is just 0. So what we're going to do, I'm going to write it right here, is I'm going to add it. So this is technically legal action number 3, pretty much, right? I am adding a multiple onto this. So let's go ahead and add it, right? So legal action number 3, I will be adding this equation to this equation, this multiple equation here to this equation. So if we add these two equations, 10x plus 3x, that's going to give us 13x. Okay? If I add this is just 0. So that's just 0. So we can just put it equal here. And then 16 plus 4 is 20. Divide 13 to both sides, you get 20 divided by 13. Okay? Now, the problems I'm going to give you is less nasty than this. I just made this up. So, yes, the answer is nasty, but on your problem sets, it will be cleaner. I just made this up, so of course it's going to become nasty. And so now that we solve for x, how do we solve for y? So what we do is we just plug in x here. So let me draw an arrow, right? You can choose which one you want to choose. I'm going to choose this one because it looks less nasty, in my opinion, but I could be wrong. 3. See, so we know what x is, right? It's 20 over 13, right? We have minus 4y. This is equal to 4. Okay. This, I don't know what this is. This is like 60 over 13. Disgusting. I'm going to swap both of this. So we have, oh god, that was a big lag. 60 over 13. Minus 4. Which equals to 4y. You can use a calculator. I'll let you use a calculator. I do not have a calculator with me, so I'm just going to solve this by hand. 2 over 13. So this is my answer. And there you go. We just solved our system of equation using legal action 1, 3. Legal action 2 just means like you swap places. Like legal action number 2 would be, oh, okay, well, I don't like the form of this, so I'm just going to swap places. 3x minus 4y equals 4. 5x plus 2y equals 8. That's literally legal action number 2. You just switch places. It looks useless, but you'll start to understand why we'll do it when we have a lot more, and it'll get uglier. But don't be afraid. We'll conquer that. So, but yeah, it's useless only because we only have 2 equations. But sometimes in linear algebra, we can have like so much more, a lot more equations in our system. But for now, this is how we use our legal actions. Okay? All right, let's clean this up because man, that was nasty. I just made that problem up. So it would not look like that. Now, let's do something a little nicer, shall we? Because that was nasty. So here, whenever you see a variable that does not have a coefficient. So what I mean by coefficient, let me grab a marker. So what I mean by a coefficient means this 3 and this 4 and this 2, right? This 3 is a coefficient for this x. This 4 is a coefficient for this y. That's what a coefficient means. Now, if you see a variable that does not have a number next to it, that does not have a coefficient next to it, then we're going to do something nicer. We're going to do something much less nasty. Okay? Here, because this x is lonely, what I'm going to do is I'm going to rearrange it. That's an ugly arrow, but pretty much I'm going to rearrange it as x equals, and I'm going to put this to the other side. So we have x equal 8 minus 2y. Okay? Now that we have x equals 8 minus 2y, I'm going to use a different marker, and you'll see why. Well, actually, let me go like this. So we have 3x. Here we have 3x minus 4y equal 4. I'm just going to rewrite this. And we can actually plug this into here. So whenever you see some variable that does not have any number next to it, we can turn it into this and just shove it in whatever this equation says. So we'll have 3, and I'm going to write parentheses, 8 minus 2y. Minus 4y equals to 4. Okay? So it'll look like this. Now, here, if you know, again, you must be very comfortable with your algebra. So we distribute 3 times 8, 24. 3 times negative 2, that's a negative. So this would be negative 6y minus 4y equal 4. And then you just simplify everything. So in this case, we have negative 10y. We have 24. 24 minus 10y is equal to 4. We'll take this, subtract 4 to the other side. We'll get 24 minus 4 is 20. We'll shove this to the other side. 10y. And when we divide 10 to both sides, you can easily see that y is equal to 2. Okay? A little less clean. I'm sorry. A little more clean. The previous one was nasty. But this is a lot cleaner, a lot nicer. So now, again, this came from this. Okay? So, now that we know that y is equal to 2, we can literally just plug it in. Now we shove it into this equation, and we get x equals 8 minus 2y. Again, y is equal to 2. So we have 2 now. And so x is equal to 8 minus 4. X is equal to 4. So our solution is x equals to 4, y is equal to 2. And this is our answer. Okay? And that's it. That's all we have to do. A lot nicer. A lot nicer than the last problem. Okay. And sometimes we can have something missing here. It would just be equals to 2. Right. So sometimes systems can look like this. Now we're really getting into linear algebra territory. But don't freak out. Don't freak out. Okay. Again, I notice that we have some variables lonely. Because in this equation, this variable is lonely, I'm going to use y instead of x. So I'll use y. So to do this, I'm going to rearrange this equation here. Since y is lonely, we'll go ahead and let y. So again, I'm just rearranging this equation, this top equation here. So I'm going to move everything to the other side. Y is equal to 2z minus x plus 5. Okay, so we're just kind of rearranging this equation here. Okay, and now that we have this, we can go ahead and plug it in here. All right, so we'll go ahead and write this as, you grab this pen. This is 2x plus y. Y is now 2z minus x plus 5, right? You can put parentheses if you want. I'll do that for your comfortability. And then here is equal to 2. Okay? So now what we have here, we just, again, all we have to do is simplify it, right? So we have x, we have plus 2z, and this 5 can just go to the other side, to negative 3, right? Is that what I have? In fact, we isolate x, actually. We isolate x. So this would be, so x is equal to negative 2z minus 3. Now, here's the truth about linear algebra. Sometimes we can't always solve for any variable. We will end up getting something like this, where, you know, we just can't solve for, example, in this case, we can't solve for z. Okay? In fact, we can put it in terms of these variables. Let me actually continue, and you'll see what I mean. So now that we solve for x, again, we still have z, but don't worry about that. For now, we have y. Y is equal to, well, we could plug in x here, right? X is in terms of z. So y is equal to 2z minus, we have negative 2z minus 3. Let me write it like this so that you don't get confused which is 2, which is z. I'm probably triggering a lot of mathematicians who are watching this. But, let's see, at negative x plus 5. Okay. Okay. And then we simplify this, right? Y is equal to, let's see, this is 4z. And then this is plus 3. Again, that negative distributes, so it makes it positive, so don't forget about that. Okay, so the negative cancels it out. Let's see. Yeah, so we have negative, so this is now positive 3 plus 5. So our answer, we have y for z plus 8. Okay, it seems like that's exactly what I have. Yep. So what we have is we have our answers in terms of z. Now again, in this case, we do not, we were not able to find what z is. But that's okay. Sometimes we have functions, systems like this. So whenever we have a system like that, this means that this system has infinitely many solutions. I am lagging. Again, let me just kind of calibrate. Okay. So, but this is okay. It is okay. Sometimes we will come across linear systems of equations like this. This means that we have infinitely many solutions. So here's the thing. Let me write this in red. Notice that we have to put everything in terms of z. So what this means is that we say that z is a free variable. This, you're going to see this term a lot in linear algebra. Okay? We call it a free variable. Z is a free variable. A variable that we cannot solve for. But that is okay. We put it in terms of z. So z is our free variable. Okay? Now, what that means is now, since we have a free variable, that means that this has infinitely many solutions. There's like more than one solution. Infinite solutions. Okay? So how do we write our solution in infinite terms? Let me get a different marker. So the way we write our solution for infinitely many solutions is we write it as a set notation. So S. So this means like a set of solutions. That's what that is. That's what this means. So S is going to be our set of solutions. Okay? And the way we write it, because we have x, y, z, we will put it in coordinates x, y, z. Okay? And then we put our colon here, and then we put in our free variable. In this case, our free variable is z. And then we put z is any real number. That's what this mathematically means. So you'll see it like this. So this symbol just means that z is inside. I'm sorry, not inside. Z is any real number. Pretty much, that's what it means in English. So a real number just means like, it could be literally any number, like square root of 2, or pi, or e. These are real numbers. Z can literally be any real number. Okay? And the reason why we say specifically real number is, if you remember from pre-calculus, we can have complex numbers. And so, of course, we cannot have complex numbers here. It would not make sense. Why on earth we would have complex numbers in this problem? So let me erase this. But yeah, I just want to explain what this symbol means. Okay. But yeah, translating from math to English, this just means that a variable z could be any number. That's what this means. Z is any real number. Okay. I don't want to get into set theory for those mathematicians that are watching this. Okay. This is a non-math major course. Come on now. So now how do we actually write the solution? This is how we write the solution. So x is equal to negative 2z, negative 3. So that's how we're going to write it. So x is negative 2z, negative 3. Y is equal to 4z plus 8. And then z is just equal to z. Z is just z itself. For any z real number. Okay? I know it's very long, very gigantic and long, but this is our solution. Okay, let me box that in just to let you know that this is our solutions. I cannot walk any further. Okay, so I completely rewrote it because I crashed. So here we had our solution like this, right? So pretty much what this means, because we have a free variable, this means that there are infinitely many solutions, and because the system has a solution, the system is consistent. Okay, I just want to just kind of reiterate that. All right, let's go on with our next example. So we have this example. Okay, we have this. So again, we want to kind of cancel out one of the variables. So to do that, I'm going to make this, I'm going to multiply this whole equation by -2, so that -4 cancels out with this 4 when we add the two equations. So using my legal action number 1, I'm going to turn this equation, multiply it by 2. I'm sorry, -2. I'll multiply that first equation by -2. So it'll come out as -4x minus 6y equal 10. I'm sorry, negative 10. Okay. And same thing here, we just write this. Okay, 7. And then we go ahead and add these two equations, right? Okay, so if we add this, we get 0, right? So that's what we want. We want to cancel this out. And if for some reason this also cancels out too, so this whole thing, we just get 0. Okay, interesting. We have 0. So what is this? This is -10 plus 7. This is -3. Is this true? Obviously not, right? This is obviously not true. So, you know, because 0 does not equal -3, this is, in mathematical terms, we call it a contradiction, but we know this is definitely not true. 0 does not equal to -3. So, because we have this type of situation, the system has no solution. Okay, so whenever you come across a contradiction like this, it's just no solution. The system does not have a solution. No matter what you plug in, it won't fit in this equation, or it won't satisfy this system here. Okay. Now, I do want to show you something. I'm gonna use a different color. Let me use red. Okay. I'm gonna use red. I'm gonna go on this side, or maybe I'll probably put it at the bottom. Okay. So notice that we have 4x. We have 4x plus 6y. Okay. Can we actually factor a number here? We actually can. Here, we can actually factor 2 out. Right? And we get 2x plus 3y. Ah, would you look at that? This is why we have a no solution here. Because these two equations are technically the exact same equation. These two are technically the exact same equation. So, if this was equal to 5, then this should have equaled to 10. Or pretty much, yeah. This, I'm gonna erase that. This should have equaled to 10. But because it's equal to 7, we have a contradiction, which makes the system have no solutions. So, now, what if this was 10, right? What if this was equal to 10? If that was equal to 10, okay, let me write it here. Okay, so if we do end up having an equation like this, where we have 4x plus 6y equal to 10, right? Then literally, you're just dealing with the exact same equation. It's literally the same exact equation here. This is just, right? Because if you use this equation and you divide everything by 2, literally divide everything by 2, you get the same exact, you literally get this, right? If you divide everything here, if you divide this equation by 2, you literally just get the same equation as this. So in other words, you just have this in general. That's it. You literally just have this, right? That's just another form at the bottom. So because we only have this, then so in that case, instead of a system with no solution, we have a system with infinite solutions, right? Because I mean, we don't have another equation to separate x and y. So pretty much, if I isolate x, right, we get 2x, 5 minus 3y. We're doing some algebra recall here. Right? So pretty much, oops, let me grab my camera. So pretty much this x here, that's all we have. That's it. This is what we have only. That y is now our free variable. So this y here is our free variable. So because of that, we can just write our solution like this. Because we only have x and y, just write x and y. Again, we just write the format. We write the format so that you don't get lost. And then our free variable is y. So that y can be literally any number. And now we can go ahead and write our answer. What is x? X is literally this whole thing. So I might need to make a bigger set, but it's okay. I'll deal with it. 5/2 minus 3/2 y, where y can be literally any number. That's a disgusting curly bracket. There we go. So our solution would just be this. Okay? Again, right? Because these two are literally the same expression with different answers, it'll give us no solution here. So this is an inconsistent system. No solutions. However, if we follow this, right, plug in 5 and actually get 10 instead, then we literally just it's just literally the same equation. These two are literally the same exact equation, except that this is wrong, right? Because if this is 5, this is definitely wrong, because it doesn't satisfy this. So we just end up with this, because it's literally the same equation. And of course, because we only have one equation for two variables, we end up with an infinite solution. So we have an infinite solution. And so again, if it was 7, because it didn't follow this, it's inconsistent, it will give us no solution. If we do follow algebra, and this would be 10, then we have an infinite solution. It becomes consistent. I know it's a lot, but you'll get the hang of it. You'll definitely get the hang of it. Okay. But again, your problems won't be as nasty as this, because these are all just problems I just made up. Alright, let's go ahead and continue. Now that we got comfortable with system of equations, let's get to some real linear algebra stuff. So, now, what is a matrix? What on earth is a matrix? If you've taken pre-calculus, I think your teacher might have taught you what a matrix is. But just in case for those who have taken or have not taken pre-calculus, I think, well, you should take pre-calculus actually. But if your pre-calc teacher have not taught you this, that's okay. I'll show you what it is right now. So let me just give you a random example. I'm just gonna go like this, just to, I don't know, some whatever. Okay. So this is a matrix. Okay, this here is a matrix. Now, in this case, so pretty much a matrix is literally just a bunch of numbers in which we call entries. We call this an entry. It's literally just an array of numbers. So a matrix, in this case example, this is a 3x4 matrix. Okay, so that's how we kind of specify what matrix this is, right? If I asked you like, what is the size of a matrix, right? What is the size of this matrix? This is a 3x4 matrix. So a 3, which means we go by rows, and we go by columns. So there's 3 rows and 4 columns. So it's a row by column matrix. This is a 3x4 matrix. Okay, so that's it. That's literally what a matrix is. It's just this. It could be in all different kinds of sizes. Now, I do have to show you this because I'm pretty sure you're going to see this in class or in your textbook, which whatever your linear algebra teacher gives you. You'll see something like this. Do not freak out. Please don't freak out. Okay? I know this looks daunting, but let me just show you what this is. So, this is a generalized matrix. So, generally, or maybe I shouldn't write this out. Let me not write this out. It will take forever. Oops. But pretty much in general, when we have an m by n matrix, it'll look like this. This is a n. Let's be 2n. Okay. We got try not to lag. In general, this is a general. This is a general m by n matrix. Okay. So this is what you'll see in your textbook or in your linear algebra class. Don't freak out. What this is it's just a generalized matrix. This is just to generalize a matrix, right? For some random number a for entry, so we call it an entry, right? So let me write this notation. So am is, oops, god dang you stick drift. AMN is an entry number at mth row and nth column. Okay. That's all that is. That's all that is. Okay, these are just entry numbers, right? And this here is just to specify what the location, what the number is located inside this matrix. Okay? So, if you ever see this in your textbook or see this in class, don't freak out. Okay? It's just giving you what is a matrix, what does it look like, and the generalization of it. Okay? Alright. So, and these dots, it just means like however many, whatever m and n is. Okay. So now that we know what an entry is, it's notated like this. Okay. And we have an m by n matrix. Okay. Now that we know what a matrix is, let me get rid of this intimidating diagram. So matrices can be in all kinds of sizes, like I said. I don't know about a 1 by 1. Probably not a 1 by 1. That's a very useless matrix. So, matrices can literally be in any form. I don't know, let's say -2, 0, I don't know, pi, 3. So this is also a matrix. It could literally just be a row, right? It could literally just be a row. Or we can have a matrix like this, where we have just a column with other more random numbers. Root 2, e, I don't know, -1, some golden ratio. I don't know. But some more random numbers. Literally, a matrix can have any number, and it could be a size of a row or just a column. In fact, in linear algebra, we'll most likely be using a matrix in this size, and it's called a vector. But we'll learn that soon. But for now, I'm just letting you be aware that we're going to use a lot of matrix in this size. Okay. So let's clear this. So now that we know that a matrices can be in any size, filled with literally any real number, so how do we handle with nasty-ass systems, right? Let me give you an example of a nasty-ass system. Equals to 39. Oh yeah, now we're getting real nasty here. This is some real nasty stuff. A minus 6b plus c. This is why we use computers, thank goodness. Can you imagine living in the 1800s and we have to calculate this? Oh god, I would not have a math degree during that time. Okay, so we have a very disgusting system, right? So we have something like this, right? We have something like this. I'm probably a little too close. We have something like this, a very disgusting system. So how do we solve this? How do we solve something so nasty and big? How can we do this? We use what's called an augmented matrix. And let me show you how to turn this into a matrix. So, we use matrices. We're going to start with what we call a coefficient matrix. So, for those who don't remember what a coefficient is, it's these numbers here, right? Any number next to a variable, these are coefficients. Just to recall, they're just coefficients. So we have numbers right next to a variable. Any variable that's like lonely, like this a here, the coefficient is a 1, right? But obviously, 1 times the number is the number itself. So, to turn this into an augmented matrix, we'll first use the coefficient matrix. So, here we have a 1, we have another 1, we have 2. Okay, and I'm going to draw a line here. This line is like it represents that equal sign here, right? So that's what this line represents. So my big head is out of the way. So we have 2, right? This whole matrix represents the coefficients. We have -9. We got -10. These are some very real nasty coefficients to deal with. And then 1. Okay. So we have this, all right? And then here, it's these numbers, okay? It's these numbers here. So this is like a vector, pretty much, right? We have a column here. This is 39. This is -27. Okay. So this is an augmented matrix. This is, I am not tall enough. Am I kneeing down? No, I'm not. I'm just going to write augmented. Excuse my bad handwriting because I am tippy-toeing. Augmented matrix. How dare you call me short? I heard that. I can hear you behind that screen. Okay, augmented matrix. Okay, and here, this is the coefficient matrix. Is what your textbook would call it. Coefficient matrix. And this is just a vector. We just call it a vector. Right? We just call it a vector because I mean it's just a column of numbers. Okay. So that's it, right? So that's all it is. So whenever we deal with a very disgusting system right like this, right? Something you don't even want to solve by hand. You turn it into an augmented matrix. Now you're probably saying, Silver, okay, we have an augmented matrix, but how does this even help us solve the system of equations? So, here, how does it help us solve? Well, the thing is, it's less messy, right? This is the same thing as this. It's just less messier. It's just less messier. Now that we have it in the form of this, let me go. Where did I put my pencil? Oh, right here. Okay. Because this is now less messier. Okay. We can now so you remember how we used the 3 legal actions to like modify, juggle with this system of equations? We can do the same thing here. It's just a lot cleaner. That's it. It's just a lot cleaner. So much cleaner, and we could just juggle, fondle with this equation, this matrix. So now, the 3 legal actions, that we learned about in your linear algebra course or in your linear algebra textbook, they call it elementary row operations. But I just call it the 3 legal actions because it's just easier to know what it is. But just to let you know and be aware, if they call it elementary row operations, it's the 3 legal actions. That's what those are. Okay? Alright, so that's what we're going to be using with this. We'll be using our 3 legal actions. Now, let me go ahead and transfer this matrix to the other side. Trust me, you'll see why. You will see why. Okay? Believe me. Oh god. I am not ready for this, honestly. And you'll see why. Now, I'm going to mention first, I will not make you do this by hand. Okay? You will not be doing this in your problem set. You will be using a calculator. Okay? I'm going to repeat myself. You will be using a calculator. I will not make you do this by hand. Okay? The reason why I have to show you this is because, as a computer science major, you must understand what is going on behind the program. How do calculators compute such nasty matrices like this? And I'm going to show you how the program works. What is the mechanism of the process? So, this process that most calculators use, it's called the Gauss-Jordan elimination. Gauss-Jordan. If I can reach Gauss-Jordan. My arms hurt from doing this. Elimination. Oh my god. Okay. Gauss-Jordan elimination. Okay. This method is so nasty to use by hand. Okay. Again, I'm not going to force you to do this by hand. You will mainly use a RREF calculator, which you'll understand what I mean by that in the future. But for now, let me show you how this process works in calculators and computers. So, oh god, the things that you have to do as a mathematician. I'm going to use my legal actions. So, what is my goal here? What am I trying to do? So I'm gonna let you know what my goal is. Okay, I'm trying to make this nasty ass, ugly looking matrix look like something beautiful. What I mean by that, I mean like this. Okay. For some number, whatever this is. For any number A, B, C, whatever. Well, it's their letters, but you get what I mean. Some variable, right? So, in general, we want this, okay? We want this. We want this matrix, okay? However, we can't always have this, unfortunately, because we can have infinitely many solutions. So, even though it may not turn out like this, we're going to try our best to format it this way. And that's exactly what computers do. Inside the program, it will try its best to format it like this. So, that's what we're aiming for. So, again, the way this method works is we're going to try putting a 1 here and try to get as much zeros as we can, and then have a 1 here, make these into zeros, and then have a 1 here and make these into zeros. Okay, this is the Gauss-Jordan elimination process. This is the method that computers use. So now, but because I'm not a programmer, I have to force. I'm just forced to do this by hand. So let me show you how this process works. Okay, so just like the systems of equations, I will use my 3 legal actions. Let me have my paper next to me because I will cry if I do this incorrectly. So, now, notice that we have here, we have a 2, so I'm going to multiply this equation. Well, again, this line represents the equal sign. I'm going to multiply this row by -2, so that when I multiply that by -2, so the way we write the notation is -2 row number 1. Okay, this first row here is R1, row 1. Okay, I'm going to multiply this by -2, and I'm going to add this onto R2. Okay, and I want this, the result of this, I'm going to make that become R2. I'm going to make the result and substitute it in row 2. Okay, so what I'm using my third legal action. My third action, right? Adding a multiple. Oh god, I'm lagging. Just noticed that. Calibrate. Okay. I am adding a multiple of one equation to another equation. This is my third action. I just realized how long this is going to be. Oh god. Okay. So because we are only changing row 2, row 1 and row 3 is going to look the same. We'll go ahead and write our second row here. Okay, so what is this? So -2 times 1, that's -2. Add this, we get 0. Alright, -2 here, that's -2. -2 plus 9, that's 7. -2, that's 2 times -2, that's -4. -4 plus -10 is -14. -2 here is -18. -18 plus 39. This will give us 21. You see where this is going, right? Do you see the nasty process that I have to go through? I have to keep going. I have to keep going until I made everything like that blue thing that I just showed you, right? So, yeah, so we have to keep going. Again, I'm doing this so that I have 0, And then I'm gonna, you know, again, my goal is to format it like this, right? For the first column, second column, etc. Right? That's my goal. So, again, I'm close. I'm very close. This is 1, 0, and now I need this to be 0. So how do I make this into 0? I'm going to use my third action again. Or, yeah, it's technically my third action. I'm going to have this. I think I did negative row 1. I did do negative row 1. So, I'm going to multiply negative 1 to this first equation and add it to here. To add it to the third row. And the result, my result will be put into the third row. So now we go ahead again. Negative 1 plus 1, that's 0. Negative 1 plus negative 6, that's negative 7. Negative 1 times 2, that's negative 2, plus 1, that's negative 1. And then negative 1 here times 9 is negative 9, plus negative 27. That's going to give us negative 36. I am double checking because I will cry if I do this incorrectly. Okay. Again, right, it's the exact same process here. I am literally I'm almost out of the screen. So, and again, notice that we have a 7 and a negative 7. Oh, we can make even more zeros here. And so now we're going to go ahead and we're going to turn this into 0. Ah, yes, we're going to turn this into 0 by adding this row to this row. So, again, I'm gonna remind you guys, you will not be doing this by hand. Just me, okay? You will not be doing this by hand. I will make you use a calculator. If you're very bored and you want to do this by hand, go for it. Treat it like a Sudoku puzzle. But I'm warning you, it's not a fun. It's a very tedious puzzle. But I will not require you to do this by hand because in a real life situation, you're just going to be using a calculator. Okay? You'll be just using programs for this. You know, whoever enjoys doing this, like, I feel like you have to be a literal masochist to enjoy doing this because this is so tedious. All right, so second row plus third row, this would become 0. Negative 14 plus negative 1, right? That's going to give me negative 15. And then 21 plus negative 36, that's also negative 15. So again, the entire time we've been using our third action, right? Okay. So what now? Oh, it's looking a lot prettier. Notice that we have a multiple. Notice that we have negative 15s here. So we could actually divide both sides by negative 15, right? Because this is like negative 15c equals negative 15. That's what this is. So technically, we will be using our first action here. So I'm gonna use my first action of the three, our 3 legal actions. I'm gonna use my first action, multiplying a non-zero number to both sides of the equation. In fact, I'm gonna do that to both of this because I can divide 7 and I can divide negative 15. So I'm a lazy mathematician. So I'm gonna do 2 things at once. So I'm gonna do 1/7 divide. I'm gonna divide the second row, and that's gonna become my second row. And I'm gonna divide negative 15 That's also going to be my third row. Okay? So, I'm using my action number 1, and I'm doing 2 things at once because it's just easier. It's just easier to keep track, and I'm lazy, and I want to get this thing over with. So, I should hurry up before my thing crashes. God. Okay. So this simplifies to 1, 1, 2. Is this always the first row? Is always the same thing. Wow. 9 here. We have 0, 1, -2, 3, 0, 1, and 1. Okay? Alright, now what? What do we do? So now what? Well, again, our goal was to make it look like this, right? Just to recap, our goal was to make it look like this. Okay? I'm going to try not to use my eraser so that I don't lose my progress. And then, of course, I can make this become 0 by using this. I'm going to grab this equation and I'm going to subtract it to the first row. So what I'm going to do is I'll multiply the second row by -1 and then add it to the first row. And that's going to be my first row. And the reason why I'm going to make it be my first row is because when I add this, I'm going to get a 0. And I want the first row to have a 0. Okay? So that's why I'm going to put it as the first row. So, oh my god, please don't lag. Don't crash me. Okay. Just for the sake of time, I'm just going to be writing it, because you already know how this works. Oh god. We're almost there. We're almost there. Again, I'm not going to make you do this by hand. In case if you skip this video, and you're just skipping somewhere in my lecture, I'm just going to restate right now. You would not be doing this by hand. You would not be doing this by hand. You will be using a calculator for this. Okay. So that's going to be my second row. I don't know what happened to my camera. My camera just zoomed out for some reason. I don't know why. Oh, it's because I was crouching. Oh, okay. That's why. It was because I was crouching. Oh, wow. That is nice. Oh, thank God. Okay. So, oh. I wish I could bend over, but my camera will not. My camera would act funny. Let's see, 251. Okay. So pretty much, we have this here. So now, you're probably thinking, okay, Silver, we have that matrix, but what does this even mean, right? How is this going to help us? Well, let me rewrite this for you. First, let me clean this whole nasty process, and let me rewrite this to that side. Okay? Okay. So thank God, thank goodness, we have this beautiful matrix here, right? We have exactly what we want. Okay, it does not always turn out like this. It does not always turn out like this. It will sometimes have some nasty structure here, and sometimes the numbers aren't pretty as well. We can have fractions, which is worse. It is, oh god, it's terrible. But thankfully we have a very nice result here. So I lucked out, but in a reality situation, it will be so much nastier, which is why we use computers. Okay, so, but what does this mean though? Why do we want it in this form? Why do we want it in this form? because because remember that we had a system of equations. Let me turn it back into a system of equations, shall we? Right? We had A. This is 1 times A plus 0 times B plus 0 times C equal to 2. We have 0 times A, or that's very badly shifted. We have 1 times B, and this is 5, right? We have 0 times A, 0 times B, 1 times C is equal to 1, right? But, in algebra, like, if you simplify this, what does this become? Holy mackerel, what does this become? Look at this! Look at this beauty. A, and everything is 0. So A is equal to 2. B is equal to 5. And here, C is equal to 1. That is why we want it in this formation. That's why this is exactly what we want. This is a miracle, right? And because it represents variables, right? This represents A, B, and C, right? That's what it represents. This represents the variables and what it equals to, right? This variable equals to 1, this variable equals to 5. Remember that the augmented matrix, this line represents the equal signs, okay? So turning it back into a system of equations, it's so much easier, okay? So literally, again, it's the same exact process, right? This is pretty much, if we were to solve this, the system of equations that we had, right, without the matrix, it would be the same process, but you would see, variables everywhere. It's a mess, right? So we turn it into a matrix to make it look less messier, and then use our 3 legal actions. And this is what it came out. And it's this, it's exact same process. It just comes out like this, and we get our solution. Okay? And there you go. We solved the nasty system of equations. Okay? And that's the whole process. That's how your computers, that's how calculators compute a system of equations. That's how it's programmed. So that now that you understand the whole process of how it works. But I'm showing it to you just in case if your teacher decides to tell you, hey, you will be doing this by hand. I'm very sorry, but this is exactly how you solve it. Okay, it's a very tedious process. But just in case if you do have a class and your professor tells you to do it by hand, that's how you solve it by hand. I'm sorry to break it up to you, and good luck. Hopefully he doesn't, or he or she, whatever linear algebra professor you're taking, hopefully they're not too evil with their matrix that they give you. Okay. Oh god, thank goodness. Let's move along now. Let's forget we did all this. Okay. Don't actually forget. You do need to know that process. At least know how it works. In general. If you thought that was ugly, there's so much uglier. Sometimes we have a lot uglier systems of equations. Okay? However, when having or creating a calculator or programming it into solving it for us, there are 2 basic forms that it does. 2 forms of matrices. Okay? We call it echelon. It is an echelon form. To recall, an entry is a number inside a matrix. Okay? Those are entries. The numbers inside the matrix, those are entries. I'll demonstrate what a matrix looks like after writing down the rules. A row where 1 is its first non-zero entry. This is technically the leading one. That's what your textbook would call it. They call it the leading one. And I'll show you what that is as a matrix right now. So, let me go ahead. Let's see, it won't affect me, right? Please do not change, do not zoom out. Okay. Cool. So, this matrix is an echelon form. And let me show you what it looks like right now. So, it would look like this. Yes, we have, this is what an ugly matrix looks like. Pretty much, these are called the leading ones. This is a leading one, this is a leading one, and that's a leading one, right? Because for every row that we have in this matrix, the first non-zero number is a 1. This is what we call a leading one, and it is in a staircasing pattern. That's how it's ordered. Okay? So this is an echelon form, is what we call it. Row reduced echelon form. And in your graphing calculator, or some computers, programs, this is abbreviated as RREF. This is what I'm talking about. Okay? RREF. And let me show you a huge difference with this. Okay? A row reduced echelon will look like this. That's a point. Okay? So an RREF this will look like this. In computers, your program, the way your program will compute any matrix is that it will put it in a form, in echelon form first. So this is the first step that computers would do. Their first step is to put it in echelon form, and then after putting it in echelon form, we put it in row reduced echelon form. This here, this is the difference. The only difference, the biggest difference, is that now the leading ones is the only non-zero number in the column. Notice that here in echelon form, we still have non-zero numbers here and here. Here, the leading ones are lonely in this column. Okay? In fact, we have a name for this as well. Right? If you remember, this is the 1, this row starts with 1, this row starts with 1. These are called the leading ones. Here, 1 is lonely, 1 is lonely, and 1 is lonely here. Okay? We call this pivot columns. We call these pivot columns. Okay, just another vocabulary word in linear algebra, but it's okay. We'll get used to it. We'll start using that term a lot in the future. Okay, but in linear algebra, they call this a pivot column. Okay, that's all that is. It's a leading one that is lonely in a column. It's the only non-zero number in a column. They call it a pivot column. Okay, so let me delete that blue just to explain why computers do this. And the reason is because computers, they put it in echelon form because it's just a lot easier to just, add some zeros to get rid of things. And they put it in a staircase way, right? So now that we have ones and leading ones, what we do is we use it uses the third action of the 3 legal actions. It used the third action, multiply this by -4 and cancel it out, multiply this by -2, cancel it out. So pretty much it uses leading ones to cancel whatever number is above it, right? It uses these leading ones and multiply it by something to cancel this out and make it become 0. And now this gives us row-reduced echelon form. This is the process that computers uses. This is how it does. It's the, it goes to formatting, make a bunch of zeros, formatting it into echelon form, and then after it has leading ones, it puts it into row-reduced echelon form, where it gets rid of the non-zero stuff above the leading ones. And this is our result, okay? And of course we see this, it has free variables, right? There's free variables here. There's no 1 here, and there's no 1 here. Well, I mean, we have leftover stuff here. So this is what I mean by like a nastier case, right? Sometimes we don't have a staircase. We get a nastier one like this, where we get free variables. So of course, this system of equation, it has infinitely many solutions. So again, this is the step, right? It turns it into echelon form, row-reduced echelon form. Okay, and this is the type of calculator we will be using. So we have a very realistic, ugly example here, right? So again, our job is to solve the system of equations. What does A, B, C, D, and E equal? I will mention sometimes your class might write it like this. Like I'll do this bottom example. Like sometimes they'll write like, let's see, A, B, C, D. This would be like x4 minus x5 equal 3. And then C would be like x3. Sometimes your class would use this notation, but I like to use letters just because it just looks cleaner. It just looks cleaner. So hopefully your professor, I would ask your professor if you could put it in letters. Hopefully they will accept that. Okay. But as always, whenever we see a very disgusting system of equations like this, right, we turn it into an augmented matrix. So let's go ahead and do that. We turn it into an augmented matrix. And there we go. We have our augmented matrix. So now what do we do? Do we do the Gauss-Jordan elimination? Hell no, we ain't doing that. This is a Comp-Sci major course. We're gonna use a calculator. So let me drop my pen, and we're gonna find the RREF of this matrix. So let me first demonstrate how to use the RREF calculator. So you can use Python if you're advanced. You can use MATLAB. If you're a lazy person like me, if you're just some non-math major just watching this, here's what I would use. So here we will use Symbolab. Okay, so this is the website Symbolab. What you do, you just click on this white strip and it'll expand. See this matrix here? Click on that, and you click on this. Here it'll give you a size. The one that we have seems to be, let's see, that's a 4x6. So we have a 4x6 size. So our matrix size is our 4x6. I forgot to do something important. At the front, we will type in RREF, row reduced echelon form. Okay? And then here, oh god, this is then the most annoying part. We have to type in our numbers. Unfortunately, I have to do this in VR, which is the worst thing you could ever do. Oh my god, just bear with me here. 2, 4. Oh my god, it's like a remote controller. Like a TV remote, like you just have to Please use a computer. Don't use your VR like me. Oh no, come on. And then we press enter. And would you look at that? This is our row reduced echelon form. Notice that we have pivot columns here. And this is what we would use. Okay? Alright, so let's go back. Okay. So let's go back. Alright, so now that we input our calculator, the way we show our work is we just draw an arrow and put RREF. Okay. And we'll go ahead and write down our row reduced echelon form. Again, nasty as always, but again, this is what we would be doing. This is what you would be doing. Just use an RREF calculator. Okay, that's it. All right. So now that we have that, we could just literally just turn it back into a system of equations. So let's go ahead and do that. So now let me write this in yellow. Let's write this in yellow. We'll go ahead and turn it into systems of equation. So this here means this. Okay, so now we have to isolate A, C, and D. Notice that B and E are our free variables. Okay, so let's go ahead and isolate that. So we have A equal to -6, -6, -2b, and -3e. B is just B itself. We don't have anything for B. C is equal to -2 minus E. D is equal to 3 plus E. And E is just E itself. Okay? That's what we have here. So, again, I'll write it right here. So, in blue, okay, notice that B and E are free variables. Okay, these are our free variables. Okay, and ACD, we actually do have a term for ACD. ACD are what they call leading variables. If my pencil can stop spazzing, leading variables. Okay? Right, so these are called leading variables, like I said, because ACD, they are represented as the leading ones, right? These are the leading ones, remember? In the pivot columns, we have the leading ones. What leading one does this represent? It represents A. What does this leading one represent? It represents C. This one represents D. Everything else, we don't have a variable for B and E, which is why these are what we say free variables. Okay? So, now, with that, we can go ahead. Let me go ahead and just add some space for myself. So, since that we have free variables, what does that mean? It means that the system has infinitely many solutions. And because we have a solution, the system that we have is consistent. So, let's go ahead and write our solution. We put it in terms of S, right? Because we have multiple solutions, we have to answer it as like a group of solutions, a set of solutions, okay? So we have to write it as a set of solutions. What are our variables? We had A B, C, D, and E, right? We had A, B, C, D, and E as our variables, okay? And what was our free variable, right? Our free variable was B and E. So for here, our free variables was B and E, where B and E can be any real number. Okay? Now that we have our format, now we can go ahead and write our solution. So our solution, A, what is A? A very long expression. So A is equal to -6 minus 2B minus 3E. Okay. B is just B itself. C is -2 minus E. That's an ugly E. Right? D is 3 plus E. Or E plus 3, you can write it however you want it. And then E is just E itself. Where B and E can be any real number. Could be any number. And there we go. We have this very, very long monstrosity answer. There you go. Okay. We have our answer like this. This is our answer. I can box it in. However, I'm not. My arms cannot reach. I can just go like this. And there we go. So, as you can see, we have our solution. I almost died from lagging. Almost crashed, but I'm good. Okay. But yeah, this is our solution. This is our long solution. A very long solution, but this is normal. Could have been worse, honestly. But yeah, again, we have to write it in this form, right? Where B and E can be any number, but for A, D, and for A, C, and D, it has to be in this format. That's what this solution means. For any B and E, for any number, for B and E, our solution, whatever fits in this format, plug in any B, plug in any E, this will satisfy the system of equations that we had originally. Okay? That's what this solution tells us. Okay. So yeah, infinitely many solutions for any number you plug in for B and E. Okay. Awesome. Cool. Thank goodness. Thank goodness we have an RREF calculator. This could have been worse. Alright. Cool. So this is our solution. Let's go ahead and erase this. Now, I will show you one thing. Oh, let me take blue out. There we go. Let me show you one thing. There's one matrix that I have to mention. When solving a system of equation, okay, when you come across something like this, let's say you put it in an augmented matrix and you do RREF, and then you end up getting this very nasty, well, it's not really that nasty, but this here, right? This something weird here. This means 0, right? 0 times A, 0 times B, 0 times C. This whole equation is 0. This portion here, let me actually use a different color, just to help visualize, right? So this here that you see, okay, this means 0 equals to 1, right? Is that true? Obviously not, right? This is completely false. So, because we have this issue here, there is no solution to the system. We have an inconsistent matrix here, right? So whenever you see something like some number with 3 zeros, but this one's not 0, it's a number, then this system does not have a solution, right? The answer, there's no solution to this answer. Okay? Just want to mention that. So we have an example problem here. what values of A, B, and C makes the system consistent, right? So what does it mean to be consistent? It means that A, B, and C has to be some number where the system does end up having a solution. It could be either a unique solution, which means like A equals this and that exactly, and then we can have an infinite solution where we have free variables. Those are two types of consistent systems that we can have. So to make sure that this isn't inconsistent, what we do is we use row reduced echelon form, right? So we calculate the RREF of this matrix. So let's go ahead and calculate the RREF of this matrix. Let me go ahead and do the computer thing with you guys just for realistic purposes. Okay? So again, we have matrix. For us, we have a 3x4, which is the most common matrix size that we will deal with. Either a 2x3 or a 3x4. But here, we have a 3x4. So let's go ahead and do that. We'll plug it in, type it in. That is very interesting. It used Gauss Jordan. That is very interesting. Did I miss input something? 251 ABC. That is very weird. So, I mean, this portion here is correct. Here, I'm very lost. 3x4. I just typed in like the RREF calculator in the website. Alright, what does it say? It says what the hell? Okay, so it should stop here. So it oversimplified. Well, yeah, so that's one of the errors that computers can do. They'll tend to oversimplify. They're like, oh, let's actually treat these variables like actual numbers, and they, oh god. But this is what you're supposed to get. This is what you're supposed to get right here. Okay, this is what you're supposed to get. So, so let's go ahead and put that in. So how do we know how do we make this become consistent, right? So what values of A, B, and C makes sure that the system is consistent, right? What that means is we need to make sure that this here needs to be 0. Does that make sense, right? What causes a system to be inconsistent? Contradiction. Things like 0 is equal to some random number that's not supposed to happen. Actually, this is true. 0 is a real number. Let me not write that. 3 or something, right? You know, things like this, right? If this is not 0, then, you know, the world ends. So, of course, we need... So, because of this, we need this to be 0. So, the system so this is what we write. So we write the system is consistent oh my god, I thought I was going to crash. The system is consistent when B plus C minus 3A equals to 0. Or B plus C equals to 3A. Right. This or this. They're both acceptable answers. Okay? They're both acceptable answers. So you can, I just like to write it like this just because it's just nicer. But this is what we need. So this is our solution. For any number a, b, and c, right? It must fit in this format, so that when we plug in any real number for a, b, and c, where this satisfies, then this matrix will always have a solution, right? If this does not satisfy, right? If we don't follow this rule for any number a, b, and c from over there, then we're going to end up with a contradictory result when we solve the system, and it'll become inconsistent. So again, right, we want this to be 0 because everything here is 0. So we must follow this in order for the system to be consistent. Okay? That's how you would solve these types of problems. All right, let me give you a kind of a bonus tip, I guess you could say. So this is actually considered a theorem, I guess. So we'll write theorem. So what on earth does this mean, right? What does this theorem mean, right? If you have a size like a equals m by m plus 2 or higher, right? So what that would look like, what this means is that you're going to have a lot wider rectangle, right? So let's look at the mechanism here, shall we? So, of course, when we have something so perfect like this, right? What this means is that we have a unique solution. So this is a matrix with a unique solution. Okay? So this is an example of a matrix with a unique solution, right? When we get this, oh, okay, this A is X is equal to A, Y is equal to B, Z is equal to C, something like that. Okay, right. So this is an example of an M by M plus 1, right? A 3 by 4, an M by M plus 1, whatever M number is, okay? So what happens if we follow this thing, right? What if it was M plus 2, right? What if N was M plus 2 or higher? So what you're doing is you're adding an extra column. You are adding an extra column, right? Now, here's the thing. Now you're probably thinking, wait, but you're forcing it to have an infinite solution. So if you don't want to force it to have infinite solution, make it 0, and then A, B, C, right? So technically, we can have a unique solution, right? No, we don't. Let me explain why. Okay, so if we rewrite this as a system of equations, I'm going to draw an arrow like that, okay? So that's what we have, right? But what about this? This is what? Variable, what, w? Right? But then w, this variable here, it's all 0, right? So isn't this the same thing as this? Right? Without the w, isn't this the same thing as that? Right? Isn't it the same thing? So if that's the same thing, then this is the same thing. Because it's a m by m plus 1. Right? Do you see why? So, if we add an extra column, but it's 0, then this is just a useless column. It's useless. It's just useless, right? You have x, y, z, but w here, w doesn't exist here. It's all 0. It's useless. It's a useless column. So, because of that, this is literally the same thing as this, which is why we say that for a consistent matrix, for n plus 2, right? This does not count. This does not count as n plus 2 because this is equal to this. So this is like m by n plus 1. This is a 3. This is not a 3 by 5 because this column is useless. This is still considered a 3 by 4, and this is the simplified version, okay? And so now, because of this, so let me erase. Because of that, adding a column that's not useless, right? If we have to add an actual column, if we have to actually add a column, this column cannot be 0, right? It must have some number, whatever, and you try your best. Oh, okay, how about 1? Well, guess what? That's a free variable. That's a free variable. A free variable w. You have a w as a free variable, right? That's a free variable, right? If you try using 1 here, it's still a free variable. If you try using 1 here, it's a free variable. This is still an infinite solution system. So the wider, and again, if you keep adding more columns, right? If you add more columns, plus 2 more than the number of rows that you have, then you're just gonna have more free variables. More free variables. Okay? The wider the matrix is, right? The more free variables you're gonna end up having because there's not enough rows to satisfy all your variables. And that is why this theorem satisfies. Okay? For n plus 2 or more, okay? n plus 1 is like a 3 by 4, right? A 3 by 4 or a 4 by 5 or a 2 by 3, an m by n plus 1, right? This theorem says an m by n plus 2 or m by n plus 3 or even wider, a very wide matrix. That's what this theorem is saying, right? If you have a very wide matrix, you'll always have an infinite solution. That's only if A is a consistent, right? The theorem says the matrix has to be consistent. If it is consistent and it's wide, then you'll always have an infinitely many solutions. Okay? But in general, like you can also have an inconsistent matrix, like always. You can always have an inconsistent matrix. But assuming the matrix is consistent and it's wide, you will have infinite solutions. Okay? Anyways, that's pretty much it for this lecture. Now that you know how matrices are, what matrices are, how we use it to solve very ugly, nasty systems of equations. So that's it for this lecture. I hope this is very helpful and not too boring, but at least very helpful and motivating for you to stay focused in linear algebra. So should give you a good background, a very good first step in linear algebra. Okay, I know it's a lot, but don't you worry. Again, a reminder: there should be problem sets in the description. And yeah, thank you so much for watching, and I'll see you guys in the next video. See ya.